Close your eyes for a second and imagine this. No stars, no planets, no galaxies, just an infinite, pitch-black universe. Sounds eerie, right? But from this cosmic void, the very first star emerged. It was a moment that changed everything, a light that broke the darkness. So, how did it happen? How did the first star form? Buckle up, because today we're taking a journey to the dawn of time to uncover the answer. Hi, and welcome to Stellar Studies, your window to the universe. In this video, we will also explore the cosmic family tree of stars, like the population 1, population 2, and population 3 stars, the 3 generations of stars that have shaped our universe. Let's dive into the ultimate origin story. Chapter 1, the early universe, a dark beginning. Let's start right at the beginning, the Big Bang, 13.8 billion years ago. In its first few moments, the universe was unimaginably hot and dense, a chaotic, expanding sea of energy. As it expanded, it began to cool. Within seconds, subatomic particles, protons, neutrons, and electrons formed. A few minutes later, these particles started coming together to create the first atomic nuclei, mostly hydrogen and a little helium. But here's the thing. For about 380,000 years, the universe was still too hot for atoms to fully form. Electrons were zipping around freely, scattering light in every direction. This era ended with something we call recombination, when electrons finally paired up with nuclei to form neutral hydrogen atoms. This is when light could travel freely for the first time, creating the cosmic microwave background. Essentially, the faint glow of the Big Bang we can still detect today. After that, things got quiet. No stars, no galaxies, just massive clouds of hydrogen and helium gas. This era is what we call the Cosmic Dark Ages. Chapter 2, Gravity, the universe's architect. So, how did we go from darkness to light? The answer lies in the invisible force that rules the cosmos, gravity. Even though the gas in the universe was spread out, it wasn't perfectly uniform. Some areas had slightly more density than others, and gravity began pulling these denser regions together. Over millions of years, these small clumps of hydrogen and helium grew larger, attracting more and more material. The process is called gravitational collapse. Imagine it like a cosmic snowball effect, tiny gas clouds merging and growing into massive ones. As these clouds grew, they started to collapse under their own weight. When gas compresses, it heats up. Deep in the center of these collapsing clouds, temperatures began to soar, millions of degrees hotter than the surface of the sun today. At these extreme conditions, something remarkable happened. Hydrogen atoms began to fuse together, forming helium and releasing an immense amount of energy. This is the moment we've been waiting for. Nuclear fusion ignited, and the first star was born. Chapter 3, Population 3 Stars, the First Giants. The first stars, known as Population 3 stars, were unlike any stars we see today. Why? Because they formed from pure hydrogen and helium, with virtually no heavier elements like carbon or oxygen. This made them incredibly monsters. Some were up to 1,000 times the mass of our sun, and extremely hot, burning at temperatures of tens of millions of degrees. These stars were also incredibly bright, outshining most modern stars by orders of magnitude. They also burned extremely hot, with surface temperatures exceeding 50,000 Kelvin, more than 8 times hotter than the sun. But they were short-lived. Because they were so massive, they burned through their fuel quickly, living for only a few million years before exploding in spectacular supernovae. In their cores, nuclear fusion transformed hydrogen and helium into heavier elements like carbon, oxygen, and nitrogen. But these elements remain trapped inside the star until the very end of its life. They end their lives in a violent supernova explosion, or even collapse directly into a black hole. These explosions scattered the newly forged elements into the surrounding space, enriching the gas clouds from which future generations of stars would form. This process, known as chemical enrichment, set the stage for the formation of Population 2 stars. Chapter 4, Population 2, the Next Generation Stars. Population 2 stars were no longer made of just hydrogen and helium. They now contained traces of heavier elements forged in the cores of the first stars. This slight increase in heavier elements changed how these stars formed and evolved. Population 2 stars were smaller and longer lived than their predecessors, meaning some of them still exist today. Many of them are found in the halos of galaxies and in ancient globular clusters, orbiting the centers of galaxies like relics of a bygone era. However, while they contained more metal, a term astronomers use to describe elements other than helium and hydrogen, than population 3 stars, they were still metal poor compared to the stars we see in the Milky Way's spiral arms today. This meant they were unlikely to form planets, as planets require heavier elements like silicon, iron, and carbon. Still, these stars were crucial. They enriched space with even more heavy elements, setting the stage for the formation of the most familiar type of stars, population 1 stars. Chapter 5. Population 1. The stars that built worlds. By the time population 1 stars began forming, the universe had undergone billions of years of stellar evolution. The gas from which they formed was now rich with metals, thanks to countless generations of exploding population 2 and 3 stars. This change had a profound impact. Population 1 stars, like our Sun, are the most metal-rich of all, meaning they have the essential ingredients to form planets, moons, and even life. These stars are found in the spiral arms of galaxies, where star formation is still actively happening today. Because they contain a high percentage of metals, they are the ones most likely to host planetary systems. Our own solar system is proof of this. Everything we see around us, from the iron in Earth's core to the carbon in our bodies, was once forged in the hearts of earlier generations of stars. Chapter 6. Why does this matter? The first stars were more than just bright lights in the dark. They were the universe's first creators. Their light marked the end of the cosmic dark ages, and their end seeded the cosmos with the materials needed for everything we see today. Each generation of stars has contributed something crucial. Population 3 stars created the first heavy elements. Population 2 stars helped build galaxies. Population 1 stars made planets and life possible. Today, telescopes like JWST, James Webb Space Telescope, are searching for light from the earliest stars and galaxies, hoping to reveal clues about the universe's first moments. From the first brilliant giants of population 3 to the life-giving stars of today, each generation of stars has played a big role in shaping the cosmos. Think about this. Every atom in your body, every bit of carbon in your DNA, the oxygen you breathe, the calcium in your bones, was forged in the core of a star. In a way, those first stars are our cosmic ancestors. Without them, none of this, galaxies, solar systems, Earth, life, or even stellar studies would exist. Conclusion. Mind blown yet? The story of the first star is just one chapter in the epic tale of our universe. If you want to uncover more cosmic mysteries, make sure to hit that subscribe button and join the Stellar Studies crew for more space-filled adventures. And hey, we'd love to hear from you. Drop a comment below and tell us, what's your favorite space mystery? Let's spark a cosmic conversation. Until next time, keep your eyes on the stars and your curiosity soaring. This is Stellar Studies signing off. See you in the next video.